on the implementation side. Don't usually trust this. Okay, so who's not in class?
Go back your place and don't say no class. So you again. Then you find big.
Oh, okay.
Okay, so this morning we'll be talking about the alpha beta folding, right? That's what we're going to start with, the alpha beta folding. Yes. So if we can remember, when we're performing, like when we get f of a, b, c, right, and the verifier sends a randomness for a. So basically f of a, b, c is add I, a, b, c, right, times wb plus wc, right, plus more I, a, b, c, wb times wc, right? So the verifier sends randomness for a, and when we evaluate the polynomial at that randomness, we get f of bc, right? So we're meant to now perform sum check over f of bc. Does it sound strange? It doesn't, right? So we're meant to perform sum check over f of bc. Add I evaluated at a, b, c, right, times Does it make sense to this point? Yes. So after sum check, like at each round of the sum check protocol, the verifier sends a random challenge, right? Right? So at the end of the sum check protocol, we are going to have random values for b and c, right? Which we are now meant to, basically we have a random value for b and a random value for c, so which breaks down to two new sum checks, right, for wb and for wc. Is it making sense? So at the end of the sum check, so at the end of the sum check protocol, the verifier is meant to do an oracle check, right, which is basically evaluating this f of BC at the random challenges that the verifier sent. So the verifier has sent randomness for B and has also sent randomness for C. Right. So WB here is W evaluated at the randomness for B. Right. And WC is W, is still that WI, right? Evaluated at the randomness for C. Does that make sense?
Yes.
Makes sense, right? But now this WB and WC, we can think of the evaluation at one layer, we can relate it to the evaluation at the layer below it, right? So we can as well still think of WB, let's say WI of B, we can relate it to WI plus 1, right?
Yeah.
We can relate it to WI plus 1, still with the same equation.
When you say WI plus 1, are we not supposed to be going down instead of up?
Sorry.
WI plus 1 is related to WI,
Yes.
not WI is related to WI.
Yeah, sorry. Yeah. That's WI and WI minus 1.
Yeah,
Right.
minus 1.
Yeah, where we're going down.
I think it depends on how the indexing, how our indexing. So
Yeah.
yeah, now it's complete. The index now is complete with 0, 1, 2. So it's basically I and I plus 1, like you said. So if your own index is
But-
reverse, you can use I and I plus 1.
But like
Indexes
do you understand what? Okay. So well, let's take the output as, just for clarity, right? Let's take the output as 0, right? So when we are going down to the input, that is like I plus 1.
I plus 1, yes.
So it makes sense now, right? Okay. So we can represent W, or we can think of W as, or basically there's a relationship between W and WI plus 4, right? Which is still the sum check polynomial f of, that will be f of, so for B, let's say the okay, let's just, so at the end of the sum check protocol, the verifier sends randomness, right? So for B, the verifier sends randomness for B. We're going to call it RB. And for C, the verifier sends randomness for C. Let's call it RC. Right? Does it make sense? Okay. So normally we would have done two different sum check protocols, right? Trying to prove that W of R, let's say WI of RB is actually, or can actually be gotten from WI plus 1. Right? Let me just draw the circuit. Right. So we started from the output, and we proved that this output can be gotten from a relationship with this layer, the layer that fits into the output, right? And now we have claims on this layer now. Any claim on this layer can still be thought of as a claim on this layer. We agree, right? So WI can be thought of as a claim on this layer. WI can be thought of as a claim on this layer. right? And since we have two claims, which is Wi evaluated at RB and Wi evaluated at RC, these are two different claims, right, on the Wi layer. Is it making sense? So we can perform two different sum checks, right, which is basically still similar to this sum check on those two different claims to prove that there is a relationship between it and the layer beneath, right? But doing those two sum checks is, let's say, it's expensive. So we are looking for a way to reduce those two sum checks to one. Does everything make sense up to this point? Okay. So, and one way we can do that is by doing a random linear combination between these two, this guy and this guy. We perform a random linear combination between the two of them to get a new claim. So we're reducing the claim on this guy and this guy to a single claim that we can now do some check on. Because that single claim will still be a claim with respect to the layer beneath. I don't know if it makes sense. Is it making sense?
Yeah.
Please, if at any point we are confused, just ask. Okay, so
So it's random linear combination.
yeah. And alpha and beta is basically what we are going to use to perform that random linear combination. Okay. So now let's look at like how we can go about doing the random linear combination to reduce two claims on layer I to a single claim on layer I plus 1. Okay. So let's say Wi at evaluated at RB equal to, let's say B, right? Okay, let's just say B. And Wi evaluated at RC is equal to C. So if we have two random values, alpha and beta, alpha times B, right, plus beta times C should still be equal to Wi evaluated at RB, or alpha times Wi evaluated at RB plus beta times Wi evaluated at RC. Do we agree? Huh? Like, I just equated Wi evaluated at RB is equal to B. This is a polynomial, right? This is a constant or a single value, right? This too is a polynomial. This is a single value, right? So what I'm saying is that since we have this constant value, if we multiply that value by alpha and then we add it to multiplying C by beta, we should get the same thing as when we multiply alpha with this polynomial. Yes, plus when we multiply beta with this other polynomial. Huh? Okay. So this is Wi. Wi. We understand what Wi is, right? Which is the evaluation of a layer when we convert it to a multilinear polynomial. That's Wi, right? So I'm saying if I evaluate that Wi at a random number, right? When you evaluate a polynomial at a number, you're going to get a value, right? And let's say we evaluate it at RB, and then we also evaluate that polynomial at another different random value. Maybe we're going to do like an example so that it will be clear, right? To get C, when we evaluate that polynomial at RC to get C, if we multiply alpha times this result we got and we add it to, like, we multiply beta times C, right? This B and C are constant values, right? Which is basically just the evaluation of this polynomial. So any result we get here should be equal to us just multiplying the polynomial, this polynomial that gave B. We can just multiply it by alpha and then add it to the polynomial that gave us C, multiply it by beta, right? And then when we evaluate the new polynomial we get here at RB and RC, right? We evaluate this guy at RB, evaluate this guy at RC, and sum it up. We should get the same value with this guy. So these two should give us the same values. Let's do an example. So let's say we have let our Wi be 2, maybe just something simple, 2x plus 3, right? Are we together?
Yes.
And let's say our RB should be equal to 2. Let's say our RB should be equal to 5, and our RC should be equal to what should we use? 3. Let's also pick values for alpha and beta now. So what should be our alpha?
So the domain at which we pick them will be from prime field, right?
Yeah, from the prime field.
Both alpha and the random challenge.
Yes.
Alpha, beta, and random challenge.
Yes. So what should we use for alpha? Let's use 2 for alpha. How about beta? 7. Right? So what are we driving at? Wi evaluated at RB will be equal to 2. RB is 5, right? Plus 3, which is equal to 13. Wi evaluated at RC, 2, 3 plus 3, which is equal to 10. 9, sorry. Right? So this is our B and this is our C. Right? And what we are saying is that, say we still have this 2x plus 3, right? We have our 2x plus 3, right? If we multiply this 2x plus 3 by alpha, where alpha is 2, right? So this is alpha times wi rb, right? Which is this guy, alpha times wi rb. And beta times wi evaluated at rc. Okay, so this will be, what is our alpha? 2, right? What's our wi evaluated at rb? That's 2. Okay, no, I'm talking of the polynomial. 2x plus 3. But we know this x now will be rb, right? So this should give us 4rb plus 6, right? And this should give us a bit is 7, 2rc, right? So which is 14rc plus 21, right? So if we evaluate 4rb plus 6, at r equal to, at rb, what was our rb? 5. Right. Alpha. Okay.
Did you multiply that one by 8?
Sorry, you say?
Did you multiply that 13 and 9?
Okay, the 13 and 9, right?
Yeah, this one, so
Yeah. That's what I was looking at. So we've not done the alpha and the beta this thing yet. Yeah. So I think let's just do it so that we can just compare with. So alpha times b plus beta times c will be equal to 2 times 13, right, plus 7 times 9. All this be
26 plus 53.
plus 53.
63.
Okay, which is
89.
89, right? So these are rb. What was our rb? 5. So this is 20 plus 6, which is 26, right? And 14rc plus 21. What's our rc? 3 plus 21. That's 63, right? So we can see that this guy and this guy is the same, right? And this guy and this guy is the same because they're actually the same. They're actually the same thing. So if we add the both of them, that will just be 26 plus 63, which is 89. Okay, so did this make sense?
Yeah.
In this case, we're working with the evaluation values, right? But in this other case, we're working with the polynomials, right? But the both of them are still the same thing. Does it make sense? Sure. So that's basically what we're trying to achieve. That's basically what we're trying to achieve by squashing these two claims into one using randomness. So we're trying to use randomness to squash these two claims into one. I was seeing an example of how we can actually prove that when we multiply the results of an evaluation by random values, basically just scaling them, and when we scale the polynomials themselves and evaluate them, we're still going to get like the same value. So based on what we've done now, we're now going to look at how we can actually reduce this claim on WI evaluated at RB and WI evaluated at RC to a claim of W evaluated at a random value. So before we go into that, does what we have done now, does it make sense?
Yeah.
You cannot, yeah, don't worry. It's just, but like this one makes sense. Does it make sense? Okay. So let's look back at our initial claim, right? We have okay, yeah. I expect to be seen.
I have a question.
Okay.
So the reason why we perform or we want to perform some check on WI of
W
X.
of X, yeah.
So it's because we do not trust what the prover is giving us.
Yes.
Why do we constrain ourselves to that? Why not the entire FABC polynomial?
Why not the entire FABC polynomial? Actually, the verifier, to get add I and mod I, we can get it from the circuit.
So we can't lie about that.
But the verifier himself can generate the add I and the mod I because the verifier knows the circuit.
Okay. So is there a way that the verifier cannot cheat with the other
The verifier or the prover.
sorry, the prover?
Yeah, the prover cannot cheat with the add I and mod I because the verifier doesn't even care
About this.
about the prover's own.
Like the direction directly with the source of truth.
Yes, the verifier himself can generate
Okay.
the add I and
So
mod I.
that is how we constrain restricting ourselves to that
to the WBC.
I-
Yeah. Does this question make sense? Okay, so he was like, why do we need to prove, or why do we need to go further to prove WI evaluated at B and WI evaluated at C? Right? Which is, why do we need to go ahead to prove this guy and this guy? Can you see the board? Why don't we just prove everything? But the answer now is that the verifier can generate this guy and this guy. So the only thing the verifier doesn't trust is this one and this one. Is it making sense? So those are the only thing this WB is still the same thing with this one, and this WC is still the same thing with this one. Right? It's still the W polynomial for the layer beneath, right? That is feeding into that layer. So the verifier can generate add I and mod I, but the verifier cannot generate the W polynomial. So that is why we just focus on proving the W polynomial evaluated at B and the W polynomial evaluated at C. That makes sense, right? Okay, so hope no questions before we continue. So next we have F add I ABC times WB plus WC Okay, so when the like at the end of the sum check protocol, when the verifier sent the randomness, right, for B and C, now we have like RB and RC, right, and so we basically now need to prove this guy. Let's say this is I, right? Add I, this WI plus 1. Right? And this WI plus 1. Right? Because that's the layer feeding into the other. So this WI plus 1 evaluated at B. The verifier has sent randomness, right? So we have WI plus 1 evaluated at RB, which is the random values, right? And this other guy will be WI plus 1 evaluated at RC, right? So these are the two claims we now need to prove. We would have done different sum checks, right? Because this is WI plus 1 and we can link it to WI plus 2. We agree, right? That WI plus 1 can be gotten from WI plus 2. We agree. So we can now perform a sum check on the both of them to prove that they are actually linked to WI plus 2. But we don't want to perform two different sum checks. We want to perform one. So these are WI plus 1 evaluated at RB. What is the sum check equation, like if we want to prove this, what is the sum check equation we need to prove?
Summation
Equal to the summation of
F of BC
f of RB, right? RBBC. Uh-huh.
over the
Wait. Okay. Yeah. So summation of f of RBBC over the Boolean hypercube, right? So let's expand this guy now. F of RBBC. If I were to expand it, what will it be? Add I
of
RBBC, right?
open bracket
W, this is WI plus 2 now, right?
yes
Of B plus WI plus 2 of C, right? Sorry. So more I plus 1, right? RB, right? Right? BC WI plus 2 of B times WI plus 2 of C. Do we agree?
Yeah.
We agree, right? Okay. So, how about let me see if I can fit this guy to one line. Okay, so how about f of RC? It's f of RC BC, right? Is it? Like this B and C are still the same B and C, right? So it will be add I plus 1 RC, right? WI plus 2 of B plus WI plus 2 of C plus more I plus 1 RC BC WI plus 2 of B WI plus 2 of C.
Will that still be B if you're generating a random challenge for C?
Which one?
The last line.
This last line.
Yeah.
So this is RC, right? But it still has we're talking of the RC output gates now, right? It still has input of B and C, like left and right.
Okay, yeah, got it.
Makes sense, right? So do we agree with this equation? Huh? We agree. Okay. So first of all, you get up to this point. You get up to that point. So now we're trying to prove WI plus 1 evaluated at RB.
For that WI plus 1B, it's not supposed to be I plus plus C on the basis.
Sorry, where?
What's wrong with this? This ABC, the second one, that adds IABC, and there's WI plus 1B.
This one?
The WI plus 1 is that one.
Okay.
The arrows are pointing upwards. Isn't it coming from the second layer?
This one is coming from
Like
Layer
the WC
under.
from the layer on the.
WI
Plus
plus 1.
1 plus 1 after I plus 1.
Okay, no, I just brought this guy out, not like
Okay.
yeah. So here is B, right? When it was a variable, right? But RB now, what I was just trying to outline is that now we are evaluating it at the random challenge. You get?
But then the W, without W, where you're evaluating C, you don't have the I plus 1.
This one.
Like
The
when
one
the
is
arrow
pointing.
points to.
Okay, yes, sorry. I thought I
Where is
huh? But is it clear now? It's clear now, right? So basically this for RB, right? Then for WI, I'm just trying to rewrite this one so that we'll have the both of them here, right? I plus 1 evaluated at RC is the summation of F, right? RC, BC, right? So you can think of this guy as this guy, or you can think of this guy as this guy, right? So now I want to combine the both of them. We want to combine the both of them now. Let's combine the left hand side first, right? And then we are going to see how we can also apply that to the right hand side. You know, the left hand side are the actual values, right? Just like in this case. Just like in this case. Right? Are we following? Sure. So we basically have W. Want to combine WI plus 1 evaluated at RB and WI plus 1 evaluated at RC. We want to combine the both of them. We are going to use alpha and beta to do this combination. Is it clear? C'est clair? Eh? Oui, thank you. The French students. Yes. Okay.
So, this WI plus 1 at ROB and WI plus 1 at ROC. WI plus 1 at ROB is this summation F into ROB
Yeah.
BC, right?
Yes.
And WI plus 1 at ROC summation F into ROC BC.
Yes.
Okay. So combining it, we are going to run this summation and take.
So for now, let's focus on the left,
Okay. The left. Where is it?
which is this.
WI plus 1 ROB.
Yes, and WI plus 1 RC.
Yeah?
Like, see, you know this WI plus 1 RB is the evaluation.
Yes.
Then the summation is, let's say, where we are working with the polynomials. WI plus 1 at RB is, you can think of it as a constant value.
Okay.
While this summation here you can think of it as the polynomial side of it.
Okay.
Same thing with the wi plus 1 of RC.
Okay, so we are focusing on the
Yes, on the constant value
constant
side of things.
Okay.
I want to combine those constant values.
Yeah.
After combining those constant values, then we will now see how we can combine this
The
polynomial.
Alright.
Makes sense?
Yeah.
Okay. So want to combine, so I just brought them out, right? So want to combine them using A, alpha and beta.
Yeah. Okay.
So that's basically alpha times Wi plus 1 of RB plus beta times Wi plus 1 of RC. Right?
Yeah.
So basically anything we get out of here will be a constant, right?
Yeah.
Good. So now this same relation, we want this same relation to hold on the right hand side.
Yeah.
This is where things start getting complicated
The right hand
actually.
side is the more.
Eh? Both this entire equation. This entire equations. Is it making sense? So we just summed up this left hand side, right? Using alpha and beta. That's what gave us this. Right? So now this same thing we did here, we want to do it on the right hand side.
It's complicated because we are generalizing. We are not solving a natural example. For example, now, if my polynomial I'm working with is 3 variables, right? I must have gotten a well-defined polynomial. So to deal with will not be that difficult because
Actually, that's why I went this route,
yeah,
so that we can have like a picture of what is actually happening, right? But this is actually what we're just trying to replicate. In this other side, the polynomials were now
finite, like,
this guy and this other guy, right? But when we actually do this expansion, the polynomials will be much more like bigger because of the nature of the sum check we are doing. Make sense?
Yeah, but from what we have here, it's why do you say it's going to be complicated?
No, I'm not saying it's going to be complicated. I just said like right now you need to pay. If you are not paying attention before, you need to start paying attention now. If not, you can get lost.
So, because what I'm thinking basically is if we do the add and mod evaluation for a particular Wi plus 1 this thing, we can just simply like multiply the beta by everything there.
Yeah,
Then we do the
it's
same.
straightforward, right?
No, like if you mental pain. Yeah.
Okay, but it's clear.
Yeah, sorry.
Yeah, but is it possible to like have a circuit, like a visual circuit, so that when you say the left hand side, you're able to say, okay, this is the left hand side, and the right hand side, this is the right hand side.
Actually, you already have a circuit, and the left hand side is what the verifier is doing, right? And the right hand side is what the prover is doing.
Oh, when you say left hand side and right hand side, you mean verifier and prover?
Yes, you can think of it that way. You get?
So I wanted why are you saying it's going to
Eh?
I I remember in the last class, right? And so, I remember in the last class, we were talking about, I think when we wanted to do like something about product.
I'm still going to be.
Yeah, I know, but I'm trying to like connect something. So that was because we had a polynomial that we couldn't express in that short linear application. So we needed to leave it like as a product for 2 months linear. You can perform something. Right? So this one now, we're trying to add two polynomials, right?
Yeah, we're trying
It's not the
to.
way that they are combined to give us one. Or I'm going to perform
You're actually going to perform some check on
What?
that
the
combination.
linear combination of the both of them.
Yes.
Why you say it is going to be possible?
Okay, yes, because this WI will give us is the evaluation of WI plus 1 at RB, right? So it will give us a value. And WI plus 1 at RC is the evaluation of WI plus 1 at RC. It will give us a value. When we multiply alpha, which is a value, a random value, times the value we get here, we are going to get a constant, right? And when we multiply beta, which is a value, times this other value that we are going to get here, we are going to get a value. And when we add those two values, we are going to get a value. So that value now, it can be any value. I just called it a constant. Or let me call it a value, so or a result, anything you want to call it. You get
It's not the same, you can be in.
Yeah.
I was wondering why we get a particular value, why it's not going to be another polynomial. I think what we've seen since that it's going to be another polynomial.
no, like for now we're just talking of this.
This expression.
Yeah, just this left hand side now.
Okay.
You get.
But
But we're going to equate it now to this polynomial. These two polynomials now, we need to combine them the same way. So I'm just talking of like if we have these values and we do this evaluation, we are going to get a result. If we also have these two polynomials and we substitute the right values, basically we perform the sum check protocol, while still any result we get here is still going to be the same result we get when we combine these two, still following this alpha beta notation.
Okay. I thought we were combining WI plus 1, WI plus 1.
Yeah.
I didn't know it was F. It was F polynomial.
You can still think of the WI, it's still a relation, right?
Yeah, it's a relation, but what are we actually combining?
We're combining WI plus 1 evaluated at RB and WI plus 1 evaluated at RC. But WI plus 1 in itself is not just WI plus 1, right? It's
It's made up of WI plus 1.
is equal to this, right? The sum of F. You can think of it as this as WI plus 1.
Okay, the sum y is given by
Yeah. Where RB now is the output, right? And RC was summing over the Boolean hypercube. Makes sense. So is everything clear up to this point? Everything is clear, right? Okay, so now let's now work with the polynomials f of RB and f of RC. So still the same thing we did, right? We now want to get alpha times the summation, right, of f RB BC, right, plus beta times summation of f of RC BC, right? And anything we get here, these two values should be the same. right? Does it make sense?
Yeah.
Okay, so now let's expand. We now want to work with this guy, right? And we want to expand him. So, okay, so let's start with this guy. Right? Let's just start with this first guy. So that'll be equal to alpha times, okay, add I plus 2, right?
Maybe I like plus 2.
I think I like this.
No, that's add I. Okay, sorry. Yeah, add I plus 1. It's W that will be plus 2. So add I plus 1, right?
But this solution, since we are handling it,
Yeah.
it's
Yeah, the summation is still.
It is that F that you are replacing with this expression.
RBBC.
Okay, so RBBC, right?
Yeah.
Times
I plus 2.
I plus 2
B.
B plus WI plus 2
C.
C, right? Plus more I plus 1, right? RBBC times WI plus 2B, right? Times WI plus 2 of C.
This WI plus 2B, right?
Yeah,
What is it represent now?
it's representing this layer now, the evaluations of this layer. So you can think of the evaluations of the output as WI, right?
Yes.
You can think of the evaluation of this layer as WI plus 1.
Yeah. So
Right.
when you do WI plus 1B is,
Yeah, it's like the left hand, this layer now,
yeah,
the left hand
left
values.
hand. Okay, just that value.
Yeah, just that value
Why C is the value on the right
on
hand.
the right
So
hand.
if we come lower, it will be B1, B2.
It will be,
If we come lower, you know, at the bottom part we have 4 gates. We have four this thing. Now it's not there. Is 2 we have.
no, see, it's not particular to,
Okay.
it's not just particular to, it's a polynomial, you get. So we can evaluate it at anywhere. I don't know if I got your question.
Alright. So you know when we have W polynomial,
Yes,
which is the output of a particular layer,
yes,
right?
yes,
Now, when you say W, let's say we are talking about layer 2 now, right? Which
Okay.
is the last guy.
this one,
Yes. So that will be W2.
okay, yes, W2,
W2, right? So which when you say W2, it means everything on that layer.
yes.
Then when you now do W2 into B, what does that mean?
It means we are just picking the value at that particular
B.
B index.
B index.
Yes.
Okay, now for this last layer where we don't just have one Okay.
No, we're talking about a particular gate now, right?
Okay.
Sorry, are you looking at index or are you looking at value?
Eh?
Are you looking at index or are you looking at value? Because I think I should represent the index.
The R is the label, right? You can think of R as the label. So,
Sorry.
So
wait, sorry, everybody calm down. Breathe, breathe.
Give us
So, let's say we have a polynomial 2, 4, 6, 8, 10, right? And this is a W2. If we evaluate W2 at 2, what is the value we'll get? This is 0, 1, 2. We are going to get 6.
So that means the random challenge is just an index.
It's just an index.
What's it? But we are selecting it randomly.
Exactly.
So how does that random value now fit in? Because when I'm using field and we're doing random, it can just generate very
Any.
number.
So basically, we are picking a gate that is not here, a random gate. You get?
I don't understand.
Okay, see, I think, like, if I want to explain it, I may end up confusing you people. So I think let's just finish up what we're doing for now.
calm down, no adjustment.
Okay.
That B
Yes.
and that C,
Yes.
right?
Yes.
So I know that WI is W at a particular layer index.
Yes.
I understand that. But the moment you're putting B in that WI, what is that B?
You can, okay, just think of the B as the label for the particular input values. For now, like, I don't want people to get confused. You get? So for now, you can just think of it as just the normal circuit.
I think I can answer him.
Answer me, please.
So you have to know we used to get W of A at every layer by doing interpolation.
Right?
We used to get W of A at every layer by interpolating, by doing interpolation.
In circuit.
Yes, like the example we considered on Friday, the pharmacy. When we have, let's assume we have inputs, they give us value there.
Yeah.
You know, at that WI plus 1, we have a two array or two.
Yes.
So,
The moment we call
yes.
WA,
Wait,
right, we are referring to the output.
yes. So not first gate, second gate. We have two elements in the array. Then,
for
so the
this
two
one.
elements in the array, we are going to perform interpolation at A. Then, so that is where we get our W of A. Then we will now substitute B and C inside. That is how we get the polynomial of WI1 of B and C.
Okay, see, like, okay, wait. So this is,
What I said is correct.
yeah, what you said is correct actually. Since this is, you know, it can be more than that, but you just reduce it to 2 so that it will be easy for us to understand. You get? So you can think of this as a polynomial that should be, if we want to do mx plus c, right? This would be 4 plus x, right? It's not 4 plus x. Where x is 0, it will be 4. Where x is 1, it will be 4 plus 1, which is 5, right? So this is our, if this were our values, then this is our polynomial for that layer. So when we say wi plus 1 at B. If B is equal to 5, we are basically saying 4 plus 5, which is 9.
So B can be any number not related to the circuit.
No, yes, it's a random number.
Not related to the circuit.
Yes.
Oh.
Well, it makes sense now, right? So same thing like with this guy is the polynomial. Like if we want to start getting this one in coefficient form, we'll need to do interpolation and all. But it's a polynomial, right? And when we want to now evaluate it, this one will have like how many variables? Okay, say we extend it to a power of 2 and
8.
reduce. Say we have like 3 variables, right? So that B now will be like for each of those variables, we'll have a particular value for each of those variables that we can now evaluate this W2 polynomial.
Yeah, I got your answer. So B has nothing to do with
No, it
the
doesn't.
circuit. It has nothing to do with the input passed to the circuit
At all.
at all.
But the WB,
It's just like an
Circuit.
index. Yes. I just think of it.
But- but the WB will be from the circuit.
Yes, WB. The W polynomial, remove that B, X. You get? So it's W of X. Just
And S can be anything.
X can be anything.
He was talking about interpolation. When did interpolation come in?
Actually, it's interpolation we used to get this 4 plus X in the coefficient form, but you won't need to because you're in evaluation form.
Yeah, so just
When you just call dot evaluate, you're just doing that linear interpolate and evaluate stuff.
So like taking this now literally now, if we pass in this number, let's say it is 2468
Yes.
right now, we pass it into that lower input, and then say the result gives us 1 and 2. Now when we say WI like W2 of say 0, are we now the evaluation point now will it not be 0 and 1 like that index? Will it be because of the index of that point, or like are we going to say, because I'm looking at these 4 inputs now, will it not be evaluation point at 0, 0 and 0, 1 for say B1 and B2 and stuff like that?
For B1 and B2,
Yeah.
like that will be if it's 0, 0, like W2 evaluated as 0, 0, it's going to just give us 2, right? But you can think of this as 0, 0, 0, 1, 1, 0, 1, 1. Right, let's just make it 4.
Yes.
So when we say W2 evaluated as 0, 0,
Yeah.
it will give us 2.
Yeah. Like my question is it this 0, 0 that we are passing into that formula?
Yeah, that's the B.
That 0, 0 is what
That
we're
0,
passing
0
into.
is the B, actually.
That's what I was.
Yes. Is it making sense? Sure.
for my question, you said you're not finished yet, right?
Sorry, repeat the question.
Like you said we were going to be passing in indices like the labels, not the values.
Yeah, I think I just answered that now. This W2, right? You know how we got this W2 now? This W2 polynomial. This is the evaluation form you get. So we got the W2 polynomial. So if we evaluate this W2 polynomial at 0, 0, we should get 2. If we evaluate it at 0, 1, we should get 4. If we evaluate it at 500, 1000, we are going to get a random value. Right? W is a polynomial, and a polynomial you can evaluate it at any point. You get. So, but that point that we are passing in is actually like the index. For now, just think of it as
An index to get that value.
is. Yes. Is it making sense? Sure? Okay. But I've not even started though. And it's 12 already. God help us. So we've expanded this to this, right? We've expanded this to this. Okay. Okay. So if we multiply through by alpha, what are we going to get?
That's
get,
it.
we
Alpha
get,
times whatever.
we get summation alpha add I plus 1
Alpha add I plus 1
RBBC
RBBC times WI plus 2 B plus WI plus 2 C, right? Plus
mol I plus 1
alpha,
mol I plus
am I
1.
putting the brackets here?
Yeah.
Right? Plus alpha
Mol I plus 1
more I plus 1
RBBC
RBBC
WI plus 2
WI plus 2
B
B
WI plus 2 C.
WI plus 2 C. Right?
Yeah.
We agree, right?
Yes.
Okay. Let's look at beta. So this beta times WI plus 1 RC, right? FRCBC, right? Which is you guys should help me now.
I plus 1 to LCBC.
RCBC, right?
Times WI plus 2 B plus WI plus 2C.
Right?
Yeah, close bracket plus 1 I plus 1 into LCBC times WI plus 2 B times WI plus 2C.
Right?
Yeah, that equates to
Okay.
the summation into brackets beta times add I plus 1 into LCBC times WI plus 2 B
Is everybody following?
plus WI plus 2C close brackets close again.
Okay.
Beta first.
Then
Yeah.
beta
Before you.
beta before beta more
Mol I plus
I
1
plus 1 LCBC times WI plus 2 D times WI plus 2C, which equals to
Right?
Yeah.
Okay. So we're basically adding the both of them, right? So let's add them and see. Actually, the goal is that we're trying to see if it's possible to separate the like alpha and adai molai, beta adai molai. We're trying to separate it from W, right? To give the verifier the ability to do like everything with the alpha, the molai, beta, and all, so that the verifier can just rely or wait for the prover's response, which will be this WI plus 2 of B and WI plus 2 of C. I don't know if all the rambling I just did now made any sense. but we are going to actually see. Okay,
Yeah,
so
but if we add them, I think since they're literally the same, I think what it will just yield is alpha plus beta into add I plus one into how B is C. Oh,
They're not
how
the same,
B and how C
they are
are
not
not
the
same.
same.
it's not the same.
Yeah, so that would
Okay.
that would-
So let me just ramble why I just like basically we know that the verifier has access to the circuit, right? And since the verifier has access to the circuit, the verifier can generate add I and more line, right? And also the verifier is the one that samples alpha and beta, right? The random challenges. So is it possible for the verifier to do his own work by himself with the random challenges, right? Like any calculation he wants to do with add-I, molI, he does those calculations with alpha and beta, and then he just waits on the prover to send WB, WI plus 2 of B, and WI plus 2 of C. You know, WI plus 2 of B and WI plus 2 of C are the only things that the verifier will require from the prover. And he does not trust it,
yeah.
right? So that is what we're trying to get at.
So beta and alpha are just random values.
Yeah, they're just random
So
values.
the program now gives like 3 random values
Yep,
for each equation.
for each. But now, like these other ones, those other random values like RBRC, those ones are happening in some check.
Oh.
You get.
Okay.
But
Okay.
this alpha and beta to do the folding is actually happening in the GKR protocol. You get. So in our subject protocol, we already have a way of generating the RB and RC, right? Which are just the random challenges sent by the verifier in the course of the subject protocol. But when we now want to merge this add-I and the more like add-I for RB and add-I for RC, when we want to do that merging, that will actually be happening in the GKR protocol.
Yeah, since all the verifier requires is RBC and since the verifier can do the add mode and the alpha beta, and that means WBC is actually the same in both. So you can actually equate that out and then have what the verifier can do, like into what the prover is
The prover
actually
can.
sending in.
That's what we're driving at. Okay, so let's continue. We want to add them both together, right?
Okay.
Hmm.
What's common is WI plus 2B plus WI plus 2C.
Okay, so wait. So this and this, right? Let's bring them out so that we can see them clearly. But does everybody understand up to this point?
Yeah.
I have a question. Sorry for interrupting. Something that we are doing the solution over the alpha and beta so that we can give the verifier.
Sorry.
I will the solution so you can give the alpha and beta. I can give the verifier this. That's solution.
So that no, like what the prover will now need to give to the verifier will just be WI plus 2 evaluated at B and WI plus 2 evaluated at C.
Okay, the evaluation.
Yes, the evaluation, not the polynomial. So the verifier doesn't need to know the polynomial. The verifier doesn't need to know the polynomial.
Just put itself onto the last one. Let the verifier
Knows the input, exactly. So let's write that out.
Equals alpha
So that will be alpha
add
wait,
I plus 1
add I plus 1 into RB BC, right?
Plus,
WI plus 2
you are
B.
rewriting it.
Huh?
You are rewriting it.
Yeah, I'm writing it so that we can like be able to see.
Yeah.
Is there any need to write it? Let me
Yeah,
just
like
copy it.
since they are just, yeah, you can just maybe print it out.
So so we actually want to add these two guys together, right? Okay. So we have add I plus 1 RB, right?
Yes.
Here and
I like plus one answer.
Sorry, sir.
wait.
Why are you still adding the solution?
Yeah, it's still the same this thing now. Like they are still solved, right?
Yeah.
You get- So we've been doing it separately, but they are we're actually still meant to add them together. I was just doing it separately so that like we can be keeping track. You get?
Like what I'm saying is that no, the solution is like add, like what
Okay, the summation.
Yeah.
No, we're still doing both of them. Like we're summing both of them over.
Okay.
Okay.
Yeah.
Okay, what you're trying to say is that we can just use one, right?
Okay, I'm working towards it. I'm working towards it. You can still use the track. Can use the fraction.
Yeah,
Divide-
but this still
divide-
works.
Yeah.
Yeah.
Can I tell you that?
Yeah, I think this is okay. So
You combine the two of them.
yeah, I'll combine the two of them now. You know, like we've been doing it separately so that we can be able to see. But now let's merge them. So this WI plus 2B
Yeah, that
C,
was common.
right? Yeah, so it's common.
Yes.
Okay.
So they have alpha times add I 1 plus I plus 1, RBBC plus beta.
Wait,
add I.
wait, wait. So we can have what? Alpha times
Add I from I plus 1.
add I plus 1
Yes.
RBBC,
plus
right? Plus
beta.
beta
Add I
add I plus 1
RCBC.
RCBC,
Then into
in the bracket WI plus 2B
Yeah.
plus WI plus 2C.
right?
yeah. Yes. Yes.
Okay. Into WI plus 2B
B
plus WI plus 2C, right?
Yes. Plus. You can have the other one under.
Do we agree?
Yeah.
Since these two are like this is add I, right? But it's RB and RC. So we just factor these two guys. Right? And then we're going to have plus
Yeah, we should have the other one because there's another similarity again.
huh?
Plus alpha,
Okay, plus alpha
MOLI plus 1,
All I.
moli plus 1
RBBC
RBBC
plus
plus
beta,
beta
MOLI plus 1,
moli plus 1
RCBC
RCBC,
into
right?
WI plus 2
WI plus 2 V plus W,
times
Time.
sorry, WI plus 2
C.
C, right?
Yep.
So basically, we can expect this from the prover, right?
No, no summation.
Yeah, but the summation is still there. Right?
Yeah.
So we can expect that from the prover. So this guy now, we can think of a new Hadai to be equal to alpha, basically this guy.
Use capital E.
Sorry,
Capital
for the Hadai.
E.
Any reason?
No.
This one?
Yeah.
Okay. Okay. So RBBC plus right? So we can think of this as our new Hadai. Our new Hadai plus 1. Okay. Okay. So we can think of this guy as so we can think of this guy as our new Hadai plus 1. Okay? Is it clear? Sure. And for our new Molai plus 1, that will be equal to alpha times Molai plus 1 RB BC plus beta times Molai plus 1 RC BC. So, and basically the verifier can compute this by himself, right? Can the verifier compute it by himself?
Yeah.
Because the verifier knows alpha and beta, and the verifier also knows RB and RC, and the verifier also knows Hadai and Molai. So the verifier can compute this by himself.
Does the verifier choose the alpha and beta?
Yeah, the verifier is the one that chooses the alpha and beta. So with that, we now use this. We basically now perform some check on this new polynomial.
So that's giving you basically like one polynomial with. So actually, what we were combining in actual fact was the alpha, beta, Hadai, Molai, essentially.
Yeah, because it distributes out, right?
What happened to our
Oh, yeah, like they were separate, but we're then able to factor it.
So like we are saying that this alpha and beta that we are having, it won't have any effect on
No, it won't have any effect on the outcome. If we do this summation, any result we get will still be equal to, where do we write that again? Will still be equal to this guy, right? Do we agree that if this A value we got here is still equal to this I know, like it may not sync well right now. It's not.
Like, it doesn't make sense. Like, no, like, I'm trying to understand it because I like to understand the intuition first. So I understand the workings, like how you solve it and whatnot. But like the intuition behind going from that to this and then how this makes the work easier. That's what I'm trying to do.
So the point is that we are avoiding we are trying to avoid to get to perform two sum check. So instead of performing the two sum check separately, we can combine them, we can do this combination and just perform only one sum.
Only
So
one.
like that's
So I have a question.
that question that we have now. is
This
the
one.
This one.
Eh? This one.
Yes. What are we now going to perform some check on?
So it will be
We're still summing this over the Boolean hypercube. The normal subject protocol, but this is the polynomial now. Instead of us doing those two sum checks, right? Instead of us doing those two sum checks, we are going to perform sum check over this.
addition and the multiplication
Yes,
of that WI plus 2
with this guy.
You do.
So we're performing one sum check over this big polynomial now. Right.
Instead of doing two of them,
Okay, let me just use. Okay. So we're performing sum check. Right? Or basically alpha times wi plus, this was I plus 1, right? Yes. Wi plus 1 of rb plus beta times wi plus 1 of rc, right?
Is it WI plus 1 or WI plus 2?
It's the black question.
No, it's wi.
That's the
Yeah, that's the output.
Okay.
This guy. Okay.
Like now, previously, right? That WI plus 1 of R will be the claim sum for the first sum check. And WI plus 1 of RC will be the claim sum.
For the second.
So now this combination is the claim sum for the combined sum check. So this will be the new claim sum. Here we had two sum checks with two claim sums. Now we just want to have one sum check. So the claim sum will now be this linear combination of
Which is this a value here, right?
yeah.
We are adding the two claims sums together.
Yes, using that alpha beta.
So you get one region.
and the polynomial is not going to be that.
Then the polynomial will now be this big polynomial. So let me just write it out.
Makes more sense now.
Like, what's the impact of this alpha and beta? We could have just summed the two sum checks and the claim checks.
No, like if you sum it, the prover, that's what they call, I think it's grinding. Like the prover can basically grind, right, till he gets values that, yes, values that would sum up to this, to the sum of the both of them. You get, so that alpha and beta, that randomness is to throw the prover off, right, so that the prover will not be able to just pick values. I don't know if it makes sense. Nice. So this should now be equal to new addi plus 1, right, into
WI plus 2.
No, basic. Wait. Okay.
wait, sorry,
How do you add
yeah,
that as a polynomial?
yeah, new addi plus 1 bc,
Or R. It's not the same again, right?
yeah,
So just basic.
so it's just bc because like addi and the addi, this first one we're evaluating it at rb, so we'll get a new polynomial in bc, and this one was evaluating it at RC. So we'll get a new polynomial in BC. So this will now, like this new adder will now be a polynomial in BC, right? So times wi plus 2 of B, right, plus wi plus 2 of C, right, plus the new moli are BC, right, times wi plus 2 of B times wi plus 2 of C. So this is the polynomial that will now be performing sum check over this new polynomial.
Essentially, what is changing is just like the adder
And the moli. So we've been able to now reduce like those two sum checks to just one sum check, right? Does it make sense? Ah.
Yeah,
Hmm.
Yeah.
Hmm. Like, is there any particular place that
Can we relate this to this?
to the first equation, like this one now?
That first one, it's the VID is one.
This one?
First, before this FRDC, before this part,
This?
like before all of this part.
Okay.
Yes.
Okay.
No. Yes, I equation. This equation.
Okay, this one now, right? Yeah. So that is that last equation, that new adder, and this one. So like this wi plus 1 rb, which is this, is the sum of this f of rbc, and wi plus 1 of rc is the sum of this one, right? So when we combine them using that alpha and beta, right? So let's just step through everything again. So we have two claims, the claim of RB and the claim of RC. And we're trying to prove that it actually came from the layer beneath, which is the WI plus 2 layer, right? So this WI plus 1 RB of RC, if we want to relate it to WI plus 2, we need to relate it to the sum check equation, right? Which is this F of RBBC and F of RCBC. And if we expand it, we get this adder, right? Where RB is actually the output. And then BC is what we're doing sum check over, right? And WI plus 1 now, which is the evaluation of the layer beneath that layer. Yeah. At B, yes, left and right. Exactly. Plus more of RB times W of I, B, and C. Right. And also same thing for RC. RB and RC are on the same layer. Right? So this B and C are from the layer beneath. So B and C are basically the same values. That is basically why we are even able to perform the sum check. Or yeah, we can bring them together, right? So we sample the random challenge because we want to merge these two things together.
Like, I understand this what I want to get, can you go back to that first equation? So now, what we get at the end,
that equation that we get at the end is the same thing as saying f of a of this.
That thing we get at the end is the same thing as saying wi plus. Okay. Yeah, it's the same thing as saying this. Alpha times wi plus 1 evaluated at rb plus beta times wi plus 1 evaluated at rc.
Like the question is like, okay, you have this particular layer. Let's say you have layer 0, layer 1, layer 2, right? You're trying to, and let's say for layer 1, which is like w0, w1, you have w, let's say wi first and then wi plus 1. So now that f of a of comma bc, the first guy here,
Okay.
is saying add I, right? So I'm doing with the first layer now.
Oh shit. Okay.
Okay, so now we're doing like the first layer, the I, right? And then we are like saying, okay, for this I guy, we're dealing with WB and then we see like I plus
WC.
1 of like the next layer, right? So now we're now saying this WI plus 1 and represented by the WI plus 2.
Yes.
The next guy is right. So now, when we evaluate, like when we now expand this I plus 1, we get WI plus 2. When now
Yeah.
WI plus 2 is going to be like two different functions.
Yeah.
Right, so now merging it to one, you have that equation at the end.
Yeah.
Right?
Yeah.
That equation at the end, like that last equation at the end, like
Yeah.
the new add and new mod I. How does it relate to this guy? Is it that okay, we're just putting in that guy here for this WI plus 1b?
Okay. So the way it relates is based on the inputs to the layer, right? So we are saying if that last equation holds, that means the input to this particular layer, like the input to layer 0, if that last equation holds, then the input to layer 0 was actually gotten from the input to layer 1.
Okay.
You get?
Yes.
So that alpha beta, that folding, we're trying to prove that the inputs to like layer 1 was correct, right? So we compress it, right? So if that new equation holds, that means the input to layer 1 was correct, and also the input to which basically extends exactly that the input to layer 0 was also correct.
But wait. So, you know you have the LPC equation, right? That's that one, right?
Yes.
So you run some check on that. When you run something on that, you get two new things. So you know, at the end of the sum check, I think it's an R check.
Yes.
You verify cannot do the R check themselves, right? So the prover will give it evaluation of WI equals 1 at RB, and evaluation of WI equals 1 at RC, right? Trusted.
Yeah.
And the verifier will now take those two values and complete the Oracle check, right? Once it has completed the Oracle check, it's done with that F. Yes. But then it took two trusted inputs from the program. Now it's supposed to prove those two trusted inputs. They're starting afresh now. They're done with that previous layer evaluator. So now you're like trying to prove that those things that the program gave you are correct. Right? So normally you're supposed to prove it by using two assumptions. But now you merge it into one. And then you just continue. But you're not putting it back into that
this
that verify is gone. Yeah, you have already finished your Oracle check. But then you want to verify that the thing that the prover gave you to help you finish the Oracle check was correct. So that's why you're not supposed to do two sum checks. Rather than doing two sum checks, you just do one sum check. And then you continue like that.
Oh, okay. So I think I didn't get the question. So you were thinking of like where that value you get, where are you going to put it?
Yeah, exactly.
Okay, okay. No, so like if it's accepted, that means the input. Yeah, it just tells you, okay, yes, correct. Yeah, that the input is. So it's not as if you're using it to do something again.
This needs to be done for every layer.
Yeah.
For every layer.
Yeah. So, but like once you've verified layer I plus 2, there's basically no need to now like go to layer 1 and like from layer 0. Once you've done the sum check that verifies that the claim on layer 1 gives you something on layer 0. And then like based on this now, it forces you to go a layer lower. And you now perform that sum check. So when you get to layer 1, it's as if you're now doing that sum check you've done again, right? But there's no need for that, right?
So sorry, are the sum checks just helping you verify that each layer is correct?
Yes.
That's what the sum checks are.
Yeah. So does this make sense, like up to this point? At least, okay.
You said alpha and beta are random values.
Yes, random value.
Can you scroll to the down? Down. Yeah. So okay. New and so we are basically substituting a new add I plus 1 and a new mod I plus 1 into this place there.
Yeah, into this
then
place.
putting back the
W.
B and L
Yeah. And we're now performing some check
on everything.
on everything.
But also check on everything, or only the addition.
So you're performing some check on the entire.
Everything now.
But I thought you said both the prover and the verifier have the access to that new other PC and new like PC. So if
Yeah.
two of them have it, they don't have to. What they do not trust is the
What?
WI plus 2B plus WI
What the verifier does not trust.
is down.
Yeah. But the prover needs to generate the claim sum, right? And for the prover to generate the
Okay,
claim
over
sum,
this.
yes, the prover
The
needs to
claim
do
sum
this.
will be over the
Yes, will be
entire-
over
Oh,
exactly. Right? Does it make sense? This is just part 1 of 5 that we have to cover today. But does this make sense before we go into part 2?
That's part 2.
This is part 1 of 5 that we're meant to like. We have, is it 5 or 6? About 6 things we're meant to cover today. And this is just the first. So, this makes sense, right? So, up next, we'll be looking into evaluation form algebra, right? Okay. Evaluation form. Okay, so let's just look at WB, right? And plus WC. Like these are two different polynomials. Can we actually do? Okay, let's say if WB is like this one variable, right? So that will be 2 values, 2 evaluations. Let's say 3 and 5, right? And let's say WC is still one variable, right?
Yeah.
So let's say 6 and 8. Would it be right, say if we want to add these two polynomials, how can we go about it? Huh?
Add it based on the index.
If we are sure they are being evaluated by the same value.
Yeah, the both of them are evaluated over the Boolean hypercube.
Yeah.
Element wise,
Index wise.
like index wise.
Yeah, you're adding.
Serious?
Yes.
Wow.
If it's an evaluation from its index
We
value,
can't.
why can we have?
Because
Wow.
they
Let's-
don't-
No, calm down. So let's this B and C. Oh.
Yeah, we can't adhere that exactly my point because they are not the same variable.
No.
They are not the same variable. He gets. So you can't add element twice. Good and fine, the two of them are polynomials of the same length. But okay, let's just get the coefficient form and then C, right? So that it will make sense. So this in the coefficient form will be 3 plus 2x, right? And this in the coefficient form will be 6 plus still 2x, right?
2b.
Wait, is it 2?
Okay.
2x. But x here,
Why is it
x here is b and x here is c, right? So if we add these two polynomials in the coefficient form, this will give us 9 plus 2b plus 2c, right? 9 plus 2b plus 2c, which is a multilinear variable polynomial in how many variables? 2.
This is the recording.
My battery is low. No, it's still recording actually. Still recording. Linux. Okay. I think let's just pause it. Okay, so we got a polynomial in two variables, right? And to represent a polynomial in two variables, we actually need to evaluate that polynomial over the Boolean hypercube in two variables, right? So if we want to represent this polynomial, we are going to have an array with how many values? 4 values, right? So what are those values going to be? 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0, that will be 9. 0, 1, 11, right? 13. Right?
Yeah.
But you are doing it as if you are multiplying.
3 plus 9. 3 plus 9. 3 plus 6. 3 plus 8.
Yeah.
5 plus 6. I was 8 and 5.
Right.
When I calm down.
That's basically what is happening.
Okay. So, good and fine, you've seen a pattern, right? But we are going to, why does that pattern work? Right? We are going to see why the pattern works and how they can go about it. You get? But the way we are going to go about it now, we are going to blow up. But from that pattern you've seen, you don't necessarily need to blow up. Right?
Let's see the pattern.
Okay, so normally what we would have done if we did not know that the two of them were different variables, would have just added and gotten 6 plus 3, 9, right? And 8 plus 5, 13, right?
Yeah.
But this is not correct. When we add the both of them, we're actually meant to get a polynomial in 2 variables, right? So this is 3. This is 6. Right? So 6 plus 3, that is 9, right? 8 plus 3, 5 plus 6, 5 plus 8. So this is the pattern he saw. Eh? Yes. Yeah. So like this, no, this plus. But the operation looks like a multiplication operation, right? Which is not, yeah. No, this is an addition. This is an addition. Okay, let's just forget about this for now. I don't know if is it confusing or okay. So I'm saying like the pattern he saw was that when we add these two, we can as well think of it as like adding them elements wise. So we take 3, which is the first element here. We add this to 6 to get 9. Still 3, we add it to 8 to get 11. Then we come to 5. Kind of like I call it tensor addition. Oh, it is, right? Yeah. So 5, we add 5 to 6, we get 11, right? And we add 5 to 8, and we get 13. Right? This was the pattern he saw. But let's look at another way to go about it. Right? So this is the polynomial we're expecting to get. And we have WB plus WC, right? Which is 3568. Right? 2 plus 3 plus 2b and 2 plus, is it 2 plus 6 plus 2c. But in order for us to do element-wise addition, yes, recording. No, I played it back. Okay, so for us to add two polynomials together element-wise, they need to have the same number of variables, right? So this one, the same number of variables and the same variable. It's not enough for them to have the same number of variables. In this case, they had the same number of variables, right? WB had one variable in B, right? WC had one variable in C, right? Which the both of them, the array we got were two elements, but that was not still sufficient for us to do element-wise addition, right? They need to have the same number of variables, right? The same number of variables and the same variables. Does that make sense?
The same number of
Same
variables and the same variable.
Yes.
For element, this one has different variables.
Yeah, they have different variables, but they have the same number of variables. So it's not still sufficient.
Okay.
So they have to have the same number of variables and the same variable
For element-wise operation.
for us to do elementized addition.
Okay.
What's the number of variables?
That is,
Same thing.
we add based on index. Yeah. So, oh. So we saw that if we do elementary addition, this is wrong, right?
Yeah.
This is actually what we're expecting, right? This is actually what we are expecting. So this guy is 3 plus 2b, and this guy is 6 plus 2c. So one way we can add a new variable is by adding 0, right? Yes, adding 0c. So this b, right? You can do plus 0c,
Okay.
right? And this is c. We can do plus 0b, right? And when we do this, this is now a polynomial in two variables. Both of them are now polynomials in two variables, bc, bc. Which now means we can evaluate the both of them over the Boolean hypercube in two variables, 0, 0, 0, 1, 1, 0, 1, 1. So if we evaluate this guy at 0, 0, we are going to get 3, right? 0, 1. C is 1, right? But 1 times 0 is 0. So it's still what? Huh? 3. Right? 1, 0, what are we going to get? 5. And 1, 1, what are we going to get? 5. Right? If we evaluate this guy at 0, 0, what are we going to get?
6.
At 0, 1, what are we going to get?
8.
Huh?
8. 8. What was the last?
No,
This is
B.
0, 1.
This is B now, right?
This B is 0.
Right? So at 0, 1, C is the 1, right? But C is not the 1, sha. Okay, but you get the point. 8, so at 1, 0 is,
6.
that's 6, right? And at 1, 1, 8, right? So if we do element-wise addition, what are we going to get? Right? Which is if they are the same variable, you can just do element-wise addition. There's no need. No need to blow it up. But does this make sense?
Yes.
Makes sense, right? Like the same number of variables and the same variable. Like if this one was 2 and this one was 3, then we need to load the one that is two variables to make it 3. Yes. Yes. Yeah, it's already 3. Yeah, we can now do elementary addition.
What if it's not multi-linear, but it's the same
If it's multivariate, then you now start talking of like the interpolating set, right? we now start talking of like using, let's say, 0, 1, 2 instead of just 0 and 1. You get it? Okay, so this makes sense, right? But do we see any similarity between these two guys?
Yes, C.
Yes.
Yeah, 568.
This 3355, this is 6868. But why?
This is where
Why won't
so for okay, so for the first one, since C
So
is
why isn't this second one 6688?
because I think when B is the one with like zero value in the second one. So it's basically like I would say turned off in that sense. So basically like skipping. I don't know how to do that.
At the end of the day, it's the point where they are changing. So you can see even in the equation, like B is repeated, like B is having the same value for like the zeros of B are coming consecutively before the ones of B. And for C, the zeros of C are coming after the 0 comes, then the 1 value, then the 0 comes, and then the 1 value. So it's more like when we're doing the other side or where we just check like what is changing and what is where we're checking where to half it. So at this point, B is being repeated after the first value. It gets the repetition before going to the next half. But for C, which on this other side, like you first go through the value before going through the repetition.
I think I agree with what you said at first. Like B, look at the hyperview. B has 0, 0 test, so the value didn't change. And then C changed from 0 to 1. So I feel like that was well. So for the next two values, B now changed to like from 0 to 1, so the value should change. But then the next value is like 1, so B means also change. But for C, 0, 1, it changed, then back to 0 and 1, so it's flipping.
Okay, but that's also dependent on the variable that the initial polynomial was in.
Yes,
Right.
So like what I'm trying to say is like for the first one, basically there was no C. So like the polynomial basically depends on like when B was active, sort of. So that's why like for in so if you look at it, C is the one that's like 0 that has like a 0 what's it called?
Yeah, the zero coefficient.
Zero coefficient, exactly. So when since C is 0 here, it means that like we are basically yes, so C is basically the ones changing here, like 0 and 1, right? Like C changes every one step, if I would say like that.
But C, basically, like we added, C doesn't matter, right? Like it shouldn't even affect our original polynomial. You get? Since C doesn't matter basically because the coefficient for C is 0, so it doesn't matter. So it shouldn't affect the polynomial, how the polynomial was initially. You get? So even if we decide to add more, like plus 0D plus 0, this thing will expand, but it will still repeat based on B, right? Yes.
Yeah, wherever it's 0.
It's 1, right? It keeps 8, right?
Yes.
So that makes sense. So any variable we are adding doesn't affect the nature of the polynomial. It shouldn't. Right?
Yeah.
So it just gives us a bigger space.
It just I just occupying space painfully. Okay, so and we can see that based on this example and based on what we've been doing since, can we see any? So just start thinking of how your protocol is going to look like. You get
Start thinking.
eh? You should
We start thinking it now.
okay, no, not like gradually gradually, but I just wanted to like bring to our attention that like here we have something similar, right? W evaluated at B, right? And W evaluated at C. These are it's still the W polynomial, right? But when we evaluate it at it's still the W polynomial, meaning that it still has like same number of evaluation points, right? But in order to be able to add them together, we need the both of them to be of like it has to be WBC plus WBC, right? So that we can now do like element-wise addition, right? Okay, so but in the multiplication case, we know we cannot do element-wise multiplication, right? Because if we do element-wise multiplication, well, basically what I talked about yesterday, multiplying two multilinear polynomials will give us a multivariate polynomial. So we can't do that outright. We can't do that outright multiplication, right? But for the addition, we can. Okay. So, not like we can't do the outright multiplication, right? But actually, the thing is that since we are still working over the Boolean hypercube, we should still be able to do it and just pick the values over the Boolean hypercube where we are doing our summation. But if we want to represent the full polynomial to be able to evaluate it, I don't know if what I'm saying is making sense. Yeah. So if we want to like get a new polynomial that we can now evaluate, yeah, at any r, then we can't just collapse it that way to get a new polynomial.
So, so we've seen the evaluation from algebra W of B and W of C. We are in the sum. How about the other one? W of B multiplied by W of C. And we see the multiplication.
W of B multiplied by okay, this one.
Yeah. We got that W of the addition of W of B plus W of C from this place, right?
Yeah.
How about this one over the B and can we see how we place here? Maybe we can example pattern.
Okay, wait. An example.
The way you have done it, is it the same way we do it? Because I'm just curious to know.
Okay. So let's still use this guy, right?
Okay.
Right? Still our regular guy, 3 5 and 6 8. Which is 2 plus 3 plus 2b, right? And 6 plus 2c. right? So if we want to multiply these two guys, right? So that will be right plus 4bc, right? So it's still this still multilinear, right?
Yeah.
So this will give us, okay, it's already basically. So when we multiply the both of them, we're still going to get a multilinear polynomial, right? Meaning we can do element-wise multiplication, right? But we need to expand it, right? Because this one I say one variable, this one, okay, let's just, in the evaluation form, this will be 0, 0, 0, 1, 1, 0, 1, 1, right? So at 0, 0, 18, at this, BC. So SC is 1, 1, 0, and at 1, 1, that'll be 10. Right? And then this other guy, if we expand it, right? So that would be 3, 3, 5, 5, right? And 6, 8, 6, 8, right? So that will be 18, 24, right? 30 and right? Because this is a multilinear polynomial, right? When we multiply the both of them. Well, if we had a variable that was repeating, then we'll get a multivariate, right? And then this won't work.
So for multilinear, for multilinear, we always get like
No. It can give us multilinear or multivariate.
So how do we know when it's giving us non-multilinear? I think when we are giving, we only be giving it, but if from the evaluation form now, how do you know that?
No, it's based on the protocol now. You know the protocol, you get. So you know that this guy will be in B, right? And this guy will be in C. You get. Does that make sense? Because you know the protocol. So it's going to be difficult when you don't know the protocol. So you don't know if this is B and B, right? Or if it's C and C.
But B and C now will not give us a non-multilinear.
When we multiply them, yes, it will not.
Well, in the abstract sense, what we are actually multiplying is not multilinear. What we are actually multiplying is invariant. We just added a zero coefficient to make it multilinear.
No, like this B, you know, B is not just, it can be B1, B2, B3.
Sorry, let's go to the equation we used.
So, up or down?
Down. Yeah. Where is, sorry, scroll.
Okay.
Yes,
No, yeah.
go a bit.
Yeah, okay.
Here?
Yeah, 3 plus 2b plus 6 plus 2c. These are univariate polynomials on their own.
They are also
Yeah.
multilinear.
So,
I
so
don't see.
the only reason why it's giving us a multilinear is because on its own it's a univariate in coefficient form. We just added it with something to make it multilinear,
Yeah.
right?
Yeah.
If we convert this to evaluation form multilinear, it's just we converting it to evaluation form multilinear, but in the real sense of it, this is univariate.
Yeah.
So
Actually.
she's trying to say
Actually,
if
yeah.
C had the value for
If
either
C
one
had
of
the
them,
value,
it will give us a
either one
multilinear.
of them would have given us a multivariate.
Yes.
So,
Yeah.
So
Or if B was maybe B squared.
if B has something that's giving us a non-multilinear. So the reason why if you multiply both of them, it still gives multilinear because on their own they were
Univariate.
Because they don't share
Very
But
they share the same as so if you look at it, can you go to the add I, not I? So when we were doing it by hand last time,
Yeah.
we got to a point when we multiplied it and it was
It was giving us quadratic.
yeah, but that no, down.
oh,
Down. Yes, yes, yes. So you can see that new mod I.
Yeah.
We're going to be multiplying with WBC.
Yeah.
So now they are sharing the BBCC.
Yeah.
That's why
To give us that line.
but here they are not sharing.
Yeah.
But here now they are sharing. Like if we do this multiplication between these two, we are going to get a multivariate, right? Because the both of them are sharing like BC. You get? But if we multiply these two, they are different. They are different variables. You get? So it's going to still give us a multilinear, right? But then we cannot do this multiplication here
Yeah.
because now this is in BC and this is in BC as well. Yeah. So is that making sense?
Yeah.
Huh? Any questions so far? No question, right? Okay. So basically, like, based on this, do we have an idea of how we are going to do the expansion? I think we should, right? Because when we go from B to BC, we are just adding 0C, right? That 0 is not doing anything. So we are just duplicating based on B. Okay, how about a situation where we have two variables, right? Then it is for that, like, based on time. Okay, so a situation where we have two variables, right? Let's say, how should we do this? Let's say let's do 2 plus 3 plus 2 AB, right? Okay, and then so what is this other one? 6 plus 2C. Right? So this is going to have two values, right? But this guy is going to have 4 values. What is this guy value? 6 and 8. What is this guy's values? 0, 0, that's 3, 3, 5, right? No, it's still 3.
5, 5. Oh, no.
Right?
Yeah, yeah, yeah.
Okay. So if we want to add these two guys, right? How are we going to go about it?
They are not the same.
Yeah.
It's an addition possible, even though the one is evaluation from the other one is evaluation from.
No, they're both in the book.
They are both in the evaluation form, but can we add B to that guy, 0B, so I can blow it up, ABC, ABC.
Actually. So you're saying we add 0C here, right?
Yeah, this one, 0 is 0B.
Plus 0A plus 0B.
Plus 0 AB.
Huh?
No, 0 AB. 0 AB.
No, there's no music on me now.
It's not going to be very
This may actually bring some complication, but let's see. Right? So this guy, we're now going to blow this guy up. So the both of them will be 3 variables, right? 0 0 0 0 0 1 0 1 0. Right? Right? That, okay. So first of all, right? Let's. Oh, this is how we got. No, this is a new word. So let's get it in the coefficient form, right? Then we get the evaluations, so that we can have what to check back against. I'm still going to come back to that guy. I want to add these two guys. So we are going to get this 9, right? Plus 2AB plus 2C, right? Which in evaluation form will be okay, so that would be 9, right? This will still be 9. Yeah. So this will be this, this, right? Okay, so let's look at this guy. Three plus 6, 9, right? 3 plus 8, huh? You see? Why is Oraimo?
Lemu.
Okay. Okay, 11. Okay. So 3 plus 6, still 9 again, right? 3 plus 8. 3 plus 6. 3 plus 8. 5 plus 6. Eh? Is it the same? 9, 11, 9, 11, 9, 11, 11, 13. 9, 11, 9, 11, 9, 11, 11, 13. Wow. Interesting. Let's not assume yet. Yeah. Yeah, we can't assume it talk for all cases yet. We can't assume yet. But we still need to verify. You get
Delete my implementation.
eh?
Delete my implementation
Have you implemented this already?
in my head.
Oh. No, you can still implement and then test. You get. You can still implement it and then test it. So basically with this then, like if this works, then you throw away the need to blow up, which is a good thing, right? Based on your discussion with David Wong, right? Based on your discussion with David Wong, right? So no need to blow up. No, it's yeah. So the blowing up, it will be unnecessary, right? The blowing up will be unnecessary because we are just repeating values that we already have. Okay, so but we can't assume yet. Don't assume.
How do we verify?
Huh?
How do we verify?
Or we need to try it for more complex.
Let's say
No, not during this class. We still have a lot
you
to
take
cover.
this.
Yeah. And if people can us taking people on your own too, you're still going to. You get. So so once you expand this guy, right? And we added C. It was C we added, right? So what is it going to look like? What are we going to have for 0, 0? 0, 0, 0. 3, right? 0, 0, 1. 3, good. 0, 1, 0. 3. 0, 0, 0, 1, 1. 1, 0, 0. Abi, we know the particular 3 we are talking about. It's not everybody is crossing 3. Do we know the particular 3? Okay, which 2 3s are the same? Which 2 3s in this 4?
0, 0, 0, 0, 0, 1.
0, 0, 0, 0, 0, 1. These are the 2 3s that are the same, right? Because it's this.
I don't get what you mean by this.
Okay.
This first 3. So this first 3, this 0, 0. So anywhere we have 0, 0, 0, 0, we are going to replace it with 3. This first 3, right? So for 0, 0, 1, 0, 1, this is a 3, right? For 1, 0, 1, 0, and for 1, 1, yeah. 5, 5, right? Okay, how about here? How are we going to do it? You know, C is what was constant, right? And now we are adding 0A, 0B.
I'm sorry, I did not see what you are doing. Is it the first two or the last two are the
This one, okay, the first 2.
first
You know, this is A, B, C. This is A, B. And this is C. So AB, anywhere AB, as AB we have 0, 0. So anywhere AB is 0, 0, we are going to put in 3, which is this value. Anywhere AB is 0, 1, We are going to put in 3. Makes sense, right? Okay, how about this? Is 6, 8, 6, 8. This is our chorus. Is it still remaining?
No.
Okay. But did we understand?
Yeah.
So anywhere we see where C is 0, we are going to put 6. So here is 0, 0, 0, 0. So 6, 6, 6, 6. Right? And where C is 1, 1, 1, 1, 8, which is this? 8, 8, 8. Right? Okay. Right? So this will give us 9, 11, 9, 11, 9, 11, 11, 13. Right? Which is equal to what we got here. Right?
What is coefficient for?
Eh?
This coefficient for? I say coefficient. Where's the question?
No. So which is
coefficient they give us for this one.
no, it's evaluation form now. It's
Like this
evaluation.
evaluation form. Like I mean that one up there is the polynomial.
Yeah, this
Like, it was
in the
this one.
coefficient form, yes. So does this make sense?
Yes.
So basically, can I give any of you any polynomial and tell you to blow it up and you know exactly what to do?
Yes, sir.
You know exactly what to do, right?
Give an example.
Eh? So that will be take 4.
You
So
don't
we
know
still have a
like
lot to cover.
5G, 8.
This is
This is 130.
Part two
Two
or
or
five.
Meaning
Part
3.
two or
Yeah, this is
six.
part 2 of 6.
Okay, 6 now.
No, it's 6 actually.
At the end is expanding.
Eh?
An open loop. The end goes as the beginning comes in.
No, it's just for today. Oh. Not, I'm not even talking about this
No,
week.
before you say part 1 of 5.
No, it
Now
was
that
our
one has
oversight.
become 2. Now it has gone part 2 of 6.
We have like 6 topics to cover today. Yes. And this is just the second. First was alpha, beta, right? This is like evaluation form algebra, right? We still need to look at product polynomial and some check over product polynomial. Huh? To divide. That will be in PSEG, not now. Yeah. Okay, so does this make sense? This makes sense, right? Okay. So next, we'll be looking at I think this is sufficient. Sufficient for GKR. Yeah. Okay, so next we'll be looking at product polynomial. Product polynomial, let me all go for something. Okay, so we have seen, right, that we can basically collapse this guy, right? We blow him up, we make this guy like BC, make this guy BC, we add it, right? And then we make this guy BC, make this guy BC, and we multiply it, right? But now these two guys share the same variables, right? So we are now going to be looking at the product of two polynomials. Basically what we started yesterday. So this is just like a continuation of what we started yesterday.
On Friday.
Where is the month running?
And we know the weekend is short.
Eh? Okay, so this is going to be like a continuation of what we did on Friday. So we're going to review what we did on Friday, right? And then I'm first going to look at like the products of the two polynomials before we now go into like some check. Okay, products then break, right? But like everything makes sense up to this point, right?
Is this a manual?
Wait, this is with
Now after we look at the products of two polynomials, then we go for a break, right? Then when we come back, we're now going to look at like some check over a product of two polynomials.
You guys are gathering tools now.
Yes,
Tools for your GKR.
implementation. Like everything we've been doing today are things that you will need for your GKR implementation. You get. Okay, so we now want to look at how we can handle this guy, right? So we have two polynomials in the same variables. How can we evaluate those polynomials, right? And in evaluation form. So which example should we
You
use?
never know multiply.
Huh?
Multiply or evaluate.
So we're looking at two polynomials in the same variable. So we want to treat each of them as still the different polynomials. We don't want to multiply them, but we want to be able to evaluate.
Then
Yes. No, together. We want to evaluate them together, but we don't want to squash them together to get one polynomial. Don't worry. It's
You're evaluating both of them concurrently,
yes.
but individually.
But yeah, internally,
Yeah.
we are going to evaluate the both of them individually
But
and then
same
multiply
time. Okay, I'll multiply
the results. We're done, right?
You are not.
Okay. Okay, so we're going to be looking at a product of two polynomials now. So let's say we have let's say new, let's relate it. Or let's say Adai of BC, right? I want to multiply it with, let's say,
WI
WI
plus 1
plus 1
B
of BC.
of B. Okay, of
No, it's BC now, right? Because we've added those two. Like WI plus 1 of B plus WI plus 1 of C. Right? So when we add them, that's basically what we did here, right? So when we add them, we are going to get this guy. And this guy, you can think of this guy as WI plus 1 of BC.
Yeah.
Makes sense, right? Okay. So now we want to look at Adai times WI plus 1 of BC. Right. So this can be Adai, this can be Molai, it can be any I, depending on you. You get. But like, is this product now that we want to look at? Okay, so if we multiply these two polynomials, we are going to get a we're going to find they may be multilinear, right? But if we multiply them, we are going to get a multivariate. And one way we could do it was to multiply the both of them, get that multivariate, and work with the multivariate, right? Another way we can still look at it is think of them still as two different multilinear, right? But then we work with those multilinear separately. Yes, separately but together. Like, yeah. So, so okay. Let's say we have let's use three AB, right, and 2AB, right? We can think of this as 2 multilinear, or we can think of it as 6A squared B squared, right? Yeah, which is a multivariate, right? So one thing we could do is, everybody following? Sure.
Please, can we just specify the multilinear multivariate thing? Because they are multilinear, but they're also multivariate
Yeah, they're also multivariate.
before the product.
Yeah, like even after they have always been multivariate. Yeah.
That's confusing.
I think it's better to say non-multivariate.
Exactly,
Non-multilinear.
non-multilinear multivariate. Non-multivariate.
Forgive me.
Because they are both multivariate.
Forgive me, please. So so we have 2 multilinear, and we can work with those 2 multilinear, or we can decide to work with the non-multilinear. It's okay, right? That
I'll use somehow, yes,
Okay.
we know what you're talking about.
Okay, so we can decide to work with this guy, or we can decide to work with this guy. These 2 guys are working with them together under this feather. Okay. Okay, that was just to get us. No, that was just to. It seems some people are not with us. Like, it's as if some people are not with us. Huh? Olorun, Shogo, Alpha. Wait. Sorry. You know.
What did you say?
Sorry. Enough. Please. Sorry. Okay, so I need to learn Yoruba. Actually. Okay, so we can work with these 2 multilinear, or we can decide to work with the non-multilinear. Okay, so let's just do like an example, right? Say we want to evaluate this polynomial. We know these 2 polynomials are still the same thing. This and this. They are still the same thing, right?
Yeah.
So if we want to evaluate that A equal to, what should we use? 3. Okay, and B equal to 5. Okay? So we could do 3, right?
Yes.
Times 2, right?
Yes.
But it should be equal to 6, right?
Yes.
And 5.
Yes.
So this is 15 times 3, that's huh? 45. And this 30, right? So this time, so that's 1350. And this guy is
6 times 9 times 2 is 5. That's 54 times.
So which is, if they are not equal, then there's a problem. They are equal, right? Okay, good. So we can see that instead of working with this polynomial, we can decide to work with these two polynomials side by side, right? But they will still give us the same answer.
You know, when you said like working with them together, so we like playing basically just evaluating this one on its own, evaluating this one on its own, then
Exactly.
that's it. So it's separate, then when you say together, yeah, so I'm like, are you running them?
Okay. Because like you want to be able to perform, the goal is to, what we're going to do is sum, right? The sum check. We will still need to be able to do sum check over this combination, right? And like basically doing sum check over this combination is the same as, you can think of it as the same as doing sum check over this particular one, right? But when we, like after the break, when we come back, we're going to like look at the sum check. Yeah, doing sum check over this ones. But
If you were to partially evaluate the two of them, when we multiply, it still gives us the same integral.
yeah, yes, the two.
You can't really do partial evaluation, so it's really fixed.
Huh?
Doing partial evaluation, you can't really do that since it's really fixed problem.
Partial evaluation.
Yes.
I don't know if I got your question.
So explain now, we evaluated the two of them.
Yeah, full evaluation.
And then we got the question.
Yeah.
But let's say we partially evaluated the elements, we still get a non-linear material, a non-linear material.
Yeah.
By the time we multiply them together again. So that's still taking us back to the problem against as well.
No, but like if we partially evaluate, we are just going to partially evaluate the both of them and still be working with both of them. Let's look at an example. You get,
So let me, before you go to the example, so what you're basically doing is, in, let's say you have a loop that is running your display, so you can just hold them separately, but you're working at the both of them in the same loop,
in the same,
not
exactly.
separately. So
Exactly.
in that loop, you hold this one, but the same variable you're using to evaluate the first one, you're evaluating the second one at the same time. So at the end of the day, you're going to get different, the value for this and the value for this. So at the end of it, you now
Multiply them.
multiply the both of them. So it's not like you run a separate loop for one and run a separate loop for another one. So you're running both of them
The
in
same loop.
but you're working on them separately.
Exactly.
Understand?
Exactly. So let's just look at that partial evaluation. Then after we look at that partial evaluation, then I'm just going to give a hint as why it doesn't make sense to do the both of them and then sum it. Right? Or sorry, sum the both of them and then multiply it. Right? Yeah, summing this one, and then multiplying the result. It's no, like based on like the sum check stuff. Yeah. You know, some of you were saying like, are we going to sum this first one, get the claimed sum this one, get the claimed sum, and then multiply it?
That should be at the end
No,
now.
not really at the end. But let's just continue. So let's look at the partial evaluate, right? Let's look at the partial evaluate. Say we're still working with our two polynomials, right? So we're still working with our two polynomials, and we want to partially evaluate at a equal to 3, right? So how are we going to do it? This will be 3, right? Should be equal to 6, right? So this will be should be equal to 6 times 9, right? If we multiply this 2, we can see that we still get like 54b. You get. So when we want to partially evaluate, we're partially evaluating each of them, and then we're just like continuing holding them like that. We're not yet separately. Yeah. Okay. So I think the other one, like, is there any other
So
thing?
if we still do the same thing, we still come down to the same
To the
constants
same.
and constant, and we still do the same thing.
Yeah. Okay, so I think no, that's it, right? So I think like we can take a break here. Then when we come back, we'll just look at like some check over this. We'll look at some check over this polynomial, right? Yeah, and then that will now be like, okay,
This is 3 of 6, right?
yeah, this is 3 of 6. So that will be 4 of 6, yeah. 4 of 6, 5 of 6. Yeah, 4 of 6.
When are we coming back?
2 o'clock.
What? It's already.
I was joking.
Let us know the class and just go
How many? Eh? Okay, let's say 20 minutes. 20 minutes is okay, right?
Yes.
Huh? Okay, the circuit.